Let's start with the assembly language program, which is related to the branch and mm, call and written and some of the jump instructions. So we will see how these branch and call jump instructions are used in a AVR microcontroller family. So there are branch instructions used for controlling some of the programming structures in a looping environment they use. One of the example here I can just give you. So here is an example like write a program to clear R20 and then add 3 to it and then send the sum to port B. So what we basically do here is in this code, the first part is to clear R20. So that is done over here. So clearing this register R16 is done by loading, sorry, one second, yeah. So this is done over here. R20 is cleared first. So this is the first part of the thing. Then we are going to add 3 to R20 10 times. This is 10. 10 means 0x0a. So what is to be done is this value should be loaded to one of the register. So that is done over here. So you can see here, this is where we load 0x0a. That is a hexadecimal value. So that is one of the way we actually load the registers. Okay, that is in hexa and decimal fashion. Then we are going to add 3. That 3 is loaded to one more register, R21. Here is the register. Then we are going to loop this. So here what happens, I'm going to add R20 and 21, that means 0 is added with 3, then 3 is added with another 3, then 6 is added to 3, then 9 is added to 3, and so on, because it has to repeat 10 times. That is done by decrementing the count, which is in 10 or 16, and this is going to loop. Okay, this is going to come back here. So we are going to loop it, and the execution happened 10 times, and finally the value in R20 is loaded to port B. So this is how the branch if not equal instruction can be used to perform some of these, this kind of example. Then we have next another example where we are going to write a program to load this port B register with the value 55 and then complement it 700 times. So 55 is 0x 55 is 0101 and 0101. This is 55. So complement of this. So we are going to take ones complement. That's what this the complement means. That is 10101010. So this is nothing but A. This is 5. So this can be done many times. I can do this with many techniques. So let's see what techniques is used here. So I'm going to just send 55 value to a temporary register R16 here, and I'm going to send it to port because that's what it said first. I should repeat this complemented value 700 times. So how do you get this 700? I cannot load this 700 to a register as it is the value which is greater than 255, which is FF. I cannot do this, right? So what I'm going to do, I'm going to split it to 70 into 10. I'm going to repeat this 70 iteration 10 times. That's what the meaning. I will iterate 70 times, then I will whole thing repeat it 10 times. This is called as a nested looping. So we load this 10 here, which is 0x0a. So we don't have to worry about hex or decimals. If you know the decimal number, just give it as it is without 0x. So it will take it as equivalent hex value. So load it to R20, then another value 70 to R21. Now let's complement. This complement will just make the ones complement. Then that value will be loaded to port B. And the loop happens here. So this looping here, what happens is actually 70 times. And another looping that happens over here, that is 10 times. So total loop inside a loop becomes 10 into 70, which is 700 times. So that's what the question is about. So this is called as a nested looping. So this is quite useful in getting delay or getting more number of looping. You can have this kind. I can do 70, and you can do another three set of looping inside looping. So it's the same calculation, 10 into 7 into another x. But let's have a look into another program where we are going to in a RAM location 0x200, which contains 0. We are going to see whether it is 0. If so, we are going to put a value 55 to 8. So what is to be done? I should check whether the value in this location 200 is 0 or not. So how do I do? First, to take that value. Now this you see, this is a kind of an assembler directive that is used here, where the location is declared as 20. I'll use that location. I load that value to R30, temporary register. So this in R30, that 200 location value. Use this test instruction. What does it mean? It actually sets the flag. What happens? You have something in R30. Let's say I have 67 in R30. I wanted to know the flag status. Flag status will be affected only if the arithmetic operation is performed. If I perform add R30, R20, if R20 is 0, 0, then I will get 0 flag equal to 0, because I'm say any value. If you just add, so I'm just setting the flag bit. Is it the sign flag is set, or all that thing I can set it with this. So similarly, this operation is difficult. So what I'll do, instead of performing this, I'll just do TST R30. So what it does, it is doing the similar job, adding 1 0 0 0 to this, so that no value will be affected, but flags are affected. So that's how you check whether the number is equal or not. So once it is number is not equal, just move on. If it is equal, just load 55 to that location. And that's you can move only with the register. You cannot immediately move. That's the difference. Let's come to the next one where I am going to add. So all these examples are using branch if not equal, and here also you can find branch if not equal. Most of the case, this is something branch if carry that I am using now. So I will just add the number here. This is the 5 numbers to be added, and we have to put the lower byte. So what we are going to do, 0x79, 0xf5, and 0xe2. I'm going to add it. I should get my result. This I will store it in R20. Another result I will store it in R21. That's what the agenda is. How do I add? It's very simple. First, take this number, add it to 0, 0. Whatever you get, add it with this. Whatever you get, add it with this. That's how it is performed. And each time when you are adding, you keep the result in R20, and if you are getting a carry, if carry is there, if carry flag comes, just increment this register. That's what we do. So if you look at this, initially values are 0, 0. I'm just adding that 0 with 79. I'm checking this carry. Actually, this instruction is not necessary at all. Okay. So anyway, this will never happen actually. Now now things will happen only from here onwards. So this is not necessary. So now here if you see, the result of R20 will be added R16 here, R20. So the result of R20 is added back with R16. Then we will check for a carry. If there is a carry, R21 is incremented. Look at this. Then another case, here it is incremented. Twice it is incremented. And you can see what is going to happen. So here one increment, here one increment. These are the result in R21. So this is how you check for a carry and do the job. So this is about the branch instruction. There are a lot of other instructions also there, like branch on less than or greater than, or sign flag, all that things there. So you have to use depending on the situation. Now there is, apart from that, there are something called as unconditional branch instructions. Unconditional branch means you make a loop in the program without any condition. So it's called as a JMP. So if you look at this, the opcode for a jump instruction is similar, something like this. So these are the fixed code for JMP. This is fixed. This is the fixed bit of the instruction. Then what are this K? This is actually the address. This is the address for the jump. So this is K21 starts, K20, so on till K0. So the address is around 22 bits. 22 bits. That means it can handle up to 2 to the power of 22, which is nothing but 4 mega. So the memory location that this range is up to 4 mega. Okay, 4 megabyte or mega word, whatever you say. So that is a 22-bit location. So how that instruction is actually, so I'm actually specifying the absolute address. What happens is the address, if I say I have a code, let's say I wanted to jump JMP start. Then I have my code here and my start is here, which is originated at 0x100 or let's say 2000. Then I have start here and I have say LDI instruction R16, 0x20. So what happens? Jump start means this jump start is nothing but JMP 2000. That's the meaning. So JMP 200 is the meaning. That's what this jump takes. So the program counter. So this is the program counter. So PC is usually going to be here. Suddenly when jump comes, PC will be loaded with 2000 H. So this is how the jump happens. So PC will be loaded with 2000 H here, so automatically. So the program may be anywhere executing the instruction here onwards, and suddenly PC will change to any location. So that's what the value will be loaded. And if you look at the instruction size, so instruction size is actually totally, it is 32-bit now. That means it's a 4-byte instruction. Usually AVR will have 2 byte, but this is a 4 byte. You see here the first upper 2 bytes are actually the opcodes along with some address. The lower 2 bytes are the lower bytes address, so that is 0 to 15. So that's how this is the 4 byte instruction that I am talking about, unconditional jump instruction. Apart from that unconditional jump, there is a more called as relative jump. So unconditional jump, it actually loads the PC directly with the value. Whereas if you see relative jump, it jumps with the program counter. So the program counter PC will be added or subtracted with the value 2048 in that range. Anything between 0 to 2000 plus or minus 2048 range will be added or subtracted. So how it is 2048? Let's look at this. So this is going to be fixed code for RJMP, and these are the bits. So there are actually 12 bits, right? 12 bits. So indicating the address. So 2 to the power of 12 is 4 kilobyte. I should not say byte, 4 kilo, that's it. Okay. So now this 4K is divided in signed number in the signed arithmetic number. You have positive as well as negative. That means you can add up to 0 to 2047. Another is then minus 1 to, you can add up to minus 2048. This is the range. Okay, sign number. So total number is nothing but this much, 4k. So it is divided to two half, plus something minus something. So the total count should be 4k plus half minus half separate. So it will be adding. So what happens in the program? Relative jump means, so program may be executing somewhere the program counter. So what happens if I say RJMP, say 200, then PC will be somewhere here executing this. So with the PC plus 200 is done, so it will be going somewhere here. So PC plus 200. Similarly, PC minus 200 means you are going to subtract, so PC will be going somewhere here. So the execution goes there. So that's how the execution is moved in the upper and lower direction. So that's the relative jump. It's actually relative. And the instruction is actually 2 byte. This is a 2 byte instructions. It's a 2 byte instruction. Apart from that, there is something called as indirect jump, where we jump to a location based on the register value, which is Z register we say. So again, here the indirect addressing can be done up to 16-bit long. That means 2 to the power of 16 is the size of the memory location. So now again, this is going to be the absolute, because it is not plus or minus something. It's going to change directly. It's a jump. It's not relatively changing the PC. PC will be loaded with some new value. Whereas in the previous case, PC is modified, but here it is not. It is actually, PC will be done with some arithmetic operation in the previous case, but it is actually changing directly the PC. So this is a kind of a jump, but most of the time we use R jump, and even the jump JMP is quite sufficient to handle. So, but this Z register, the indirect jump will be useful for if you are going to a definite location in a systematic programming. If you have a fixed location where a job is to be performed, then probably this indirect jump is useful. Then let's go into the call instructions. So the call is nothing but a function. In C, what we say function call. So any function in the main program, so you have something called as a main program, and inside the main program you call a function. Let's say that function, say there is a function over here. Now what does function does? It goes to the routine, it executes that function and returns back to the function. So execution happens here. So the main program comes, suddenly a function is made, and then the function call happens, it goes to the function and comes back to the main program. That's what it does. So ultimately the PC should change. Correct? The PC value should change if you are going to have a function call. So how the PC, the only difference between the jump and a call is PC value should be stored in the stack memory, so that you should know where you're supposed to return in the call. Whereas in the jump instruction, you don't have to remember where you have made a jump, because you're never going to come back to the same location where the jump is made. That's the difference. Whereas the call is not like that. Call will use, again, this call instruction, if you see the format, this is a fixed bit, and if you see K21, so this is again the location, it is 4 mega location range. You can see that's where the call you can make. So again, it is a 4-byte instruction. This is a 4-byte instruction. So, And quite a lot of things there with the call. Whenever we make a call, the one thing is we should show the return address. Usually return address, that is a PC that is supposed to be saved in the stack, that will be the stack, how stacks are accessed. So stack is nothing but a memory. Okay, this is the memory, and you're going to save the values in that memory. Okay, so I can have my stack pointer somewhere here, sp. What is a stack? Stack pointer is actually, this is the stack pointer, two registers. So if I have this as 20 and 30, then this should be 20, 30 location in the RAM. Okay, then that's pointing over here, let's say. And if you wanted to save, so whenever a call is made, this stack pointer is pointed and the values of the PC is saved here. In a simple way, if I have to use a stack pointer, I suppose use push instruction. Let's say this is a push instruction. If let's say R20, I have a value 60, I use push R20. Then what happens? 20, 60 will come here. That means R20 value will be saved onto the stack. And the new SP will become 230 minus 1. Okay, one location less. That is 23. It becomes 20 or 2F. It becomes 20 2F. So this is going to be the top of the stack. This is the top of the stack. So here is the location. So the next time if you want to push, you should pop R20, then the value comes back to the R20. That's how the push and pop instructions are used. So that's how this is supposed to work in even in the call instruction. So let's have a look into some of the programs using call function. So here is a program. Actually, this part of this is actually toggle all the bits of the port B by sending this. So this example we have seen, but now actually we are toggling it certain delay. That means you send 0100. Sorry, yeah, this is supposed to be 01010101, and then you should have some delay. Then 10101010. And the delay, there should be some delay, and the whole thing has to repeat. So this whole iteration has to repeat. So that we are doing it with some function now. So in this part of the code is actually initializing the stack. Not necessary that you should do it, but usually if you recommend, it is recommended to load certain value to SP register to know which is the location that we are using for the stack. So the main program starts over here. It's very simple. You see here, 55 is rotated to R16 and then rotated to port B. So that's what one value is sent. Then we are calling a delay. So this delay is called. And then you have AA loaded to port B, again a call, and this is where I am going to loop. And in between the loop, I will be making a call. So whenever a call is made, it comes over here. It executes all these instructions. What does it happen in this instruction? It is actually, I am loading a register and I am simply decrementing it. Let me look into the deeper. So once that return is made, it goes back to this location. And again it comes back over here and goes back over here. So this is how that iteration happens. So basically this is one single infinite loop that we are making. In between I am making a call instruction. So here in this delay, how the delay is performed, this is a general delay, and you have some no operation. No operation is nothing, it does nothing. Actually it is actually giving you some machine cycle. So this is actually your spending time. I'm just actually, I should say that You are actually consuming some machine cycle, I say. You're consuming certain machine cycle with NOP instructions. So, and you're decrementing it FF times, that is 255, and this is how it works. So, this is easy to analyze, it's a real time waveform generation kind of a program. You have another code where I will be counting from 0 to FF with certain delay onto port B. And I'll be using two set of the functions here. One is to send to port B, other is to send give a delay. Okay. Again, here this part of the code is similar, and let's come over here. Okay. So your main loop is here. This is infinite loop. This is an infinite loop that we are making, correct? So how does it work? So I'm just calling one single function called display. Whenever display is made, it comes over here. And I can call this anytime, wherever I need, I can call this. And once the display is made, it increments the count that is initially 0, and it sends the value to the counted value, incremented value to this port B, and then I'm making a delay called delay again. So once the delay comes, it goes here. And finally, it returns to this and makes a continuous loop. So wherever it goes, again it goes over here and again. Okay. So delay here again, it's the same thing delay that we have seen in the previous example. Again, I'm spending some time here to delay. So every time the loop will continue, it will overflow till FF, and again till FF to 00 it overflows, again 00 to 1, 2, 3, so on, and it continuously loops. It's a simple incremental function, okay, that we make with the. So this is how the function call is made. So apart from that, we have something called as indirect call. We have seen an indirect jump. Now we are looking into indirect call. Again, here the call is made based on this register content, which is 2 to the power of 16 is the memory size. So that is the range of memory where you can define this call function. That's where the memory is. So I can just that is basically the PC will be changing its value. So call will be made directly onto this, changing the PC with this value, indirect value, and it goes to that location. So we have seen now all these, jump and call and return instruction. Now let's look at some of the basic fundamentals, how this pipelining is achieved, how these instructions are, the execution philosophy. Like usually there is something called as in the RISC processor, the instructions are pipelined. So every instructions are executed, next instruction is fetched, execution, fetching, execution happens. So there is something called as pipeline. So it is not the case that one instruction is fetched and at the same time it is executed. It is not happening that way. What happens? In initial first time, first instruction will be fetched. Second time, the previous instruction will be executed. Then the new instructions will be fetched. And so on again. The previous instruction fetched will be executed in the second cycle, third cycle, so on. So this is called as pipelining. You do in an instant 2 jobs and complete the previous job in that. That's how this goes. So this is called as a pipelining. Why it is done? It will save the execution time and performance of the controller. So the instruction execution becomes faster. Otherwise, instead of this, you have to execute 2 cycles. So this can be done with 1 cycle now. So if you see a typical example in AVR, multi-stage execution, so obviously this is a fetch happens. In execution, what and all happens? Execution, you see, execution, it will read the operands, it will process the operand, and it writes the result to the destination. So all these things are performed in this iteration. Okay, RPW, that happens in the execution. Fetching, it only takes the bytes instructions from the memory. It may be 2 byte or it may be 4 byte, and it's always multiple of 2. So remember one thing, so this will take the one machine cycle. So this iteration, so any instructions you take, the whole process of executing from fetching to execution, this time is actually called as machine cycle. Okay, that you supposed to remember. So machine cycle is actually the total time required for the instruction to complete the process of execution, starting from fetching till execution. So this one duration is actually machine cycle. This depends on how many clock pulses it takes. It may take 1 or it may take 2 clock pulses. It has to be declared by the data sheet. And if you see the instruction cycle here, that's what I need to tell you. For AVR, an instruction is always a one word or it can be 2 word. So most of the instructions will be completed with one word, which will take one machine cycle. So one word is one machine cycle. So any instruction with one word, that is 2 byte, takes one machine cycle. And if it is 4 byte, it takes 2 machine cycle. So what is one machine cycle? One machine cycle is nothing but one clock pulse. So this is one machine cycle. That is, if it is nothing but 1 over F oscillation. So if you know what is oscillation, you can find out what is a machine cycle. It's very simple. You see here, 4 different oscillation is given. I can say 1 over 8 megahertz is 0.125. That's nothing but one machine cycle if the frequency is crystal oscillator is. So any processor, any AVR will be connected with the crystal. Okay, it will be connected with the crystal. So this is the crystal. Whose it will give you the clock, because that's like a heartbeat. So based on that beat, the instruction executes. So this clock matters a lot. So if this clock speed is low, your instruction is slow. If the clock speed is high, the instruction goes faster execution. So based on this, we can decide. It will be helpful for to calculate delay and all. So we need to know this. So remember one thing: one machine cycle is 2 byte instruction, and usually all 2 byte will be one machine cycle, all 4 byte will be 2 machine cycle, and one machine cycle is 1 over F oscillation for AVR microcontrollers. So in AVR, there is something called as a branch penalty. What happens is, during some of the instruction execution, as I mentioned already, that instructions will be fetched, and then the next instruction will be executed. When you execute, the next will be fetched, also so on, it goes on. So but what happens, there is, let's say I have an instruction, say decrement R20, then I have say branch if not equal is say wait. I have something called as LDI over here. So R21, 16. Then so this will be when this is fetched. When this is fetched. For example, let's say when this is fetched, actually this will be executed. Okay. When this is executed, this will be fetched. So that's how it works. So when this is executed, this will be fetched. When this is executed, this will be fetched. Now the problem here is, we don't know where it is going to branch. It may be branched into some location here. But that time I should fetch the instruction of that, but I already fetched this. Why? That is what the branch penalty. If it is equal, it's okay. It goes like this. It will take only one machine cycle. But it goes back means it has to spend one more cycle to fetch that instruction. So it has to take two machine cycles. So that's the main difference in a branch penalty. So it happens in 5-stage pipeline, in a 4-stage pipeline. This is going to affect a lot of delay in execution. So this is what the branch penalty is. So if you look at some of the example here, for an AVR system of 1 megahertz, so there is a instruction, how this instruction takes the machine cycle. So if you look into that, here all these are one machine cycle. This information supposed to be given. Okay. So based on this information, it is one machine cycle into the number of time required for the machine cycle. So usually, as I told, one machine cycle is 1 over f oscillation. That's a very simple formula. So if the clock is 1 megahertz, it is 1 microseconds. So 1 into 1 microsecond is this time required for execution. Whereas if you see jump instruction, it is a 3 machine cycle instruction, it is said. So this 3 machine cycle instructions will take 3 into 1 machine cycle, and this takes 4 into 1 machine cycle, and this takes 2 into 1 machine cycle. So it's 2 machine cycles, so on. So you can simply multiply the machine cycle seconds value with the machine cycle count, you get the delay of execution of the instruction. So that's how you compute the delay. So these information will be given, and just remember one thing, this one, DEF, it is not an instruction. It is not an instruction, right? It is an assembly directive, that's why it is 0. Find the size of the delay of the code snippet here given. So this is something very interesting. So you can just see what is that actually that needs. It will take time for executing this. So you have instruction LDI and you have NOP instruction here. So this is 1 and NOP is 1. So what happens here? I'm going to loop this here. This is going to loop. So before that, this instruction is 1 plus this one, and you have this one, and you have this one, and you have this. Correct? So 1 plus 1 plus 1 plus. So this is one section. And the whole thing is repeated this much time. 255. And finally you have this. So depending on the value of the count that I am looping it, okay, this whole iteration, because these are the instructions that are in the loop. 1, 2, 3, 4 instructions on the loop. Those 4 instructions are looped 255 times. So this will give you the machine cycle count. So how do you calculate delay? Delay is nothing but machine cycle into time of one machine cycle, which is nothing but 0.1 microsecond here. So whatever value you get, that will be multiplied. So this, it comes around 0.1 microsecond. So it will come to 1,28,000, I guess the value will come. So that value you just multiply with 0.1, you get this one. So this is how you calculate the delay. So machine cycle count, this is the count into time of one machine cycle you do, you get the answer. You then, let's see on this. So find the delay with the subroutine. So I think it can be solved again. So what you need to do is you need to see how many times the no operation is kept. You see one, two. So this will be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13 times. So 13 times there are one machine cycle. That's why it is 13. Then plus 2 is this. It's repeated 200 times because the count is 200 here. And that is repeated. This is the total machine cycle. This value is total machine cycle. Multiply with the time of one machine cycle will give you this answer. So that's how you calculate. Okay. So it's very simple to work out. And you have something now, a toggle operation with 1 second delay. Now it's a similar exercise now. So we need to compute now. So it's a reverse engineering. So the program remains same. There is no difficulty in understanding the program. Just look at this instruction here. So how do you compute the 1 second delay? That's the problem. So the approach is I need 1 second delay. 1 second delay I need. How do I compute? So I should know for 1 second how many machine cycle required. What is the machine cycle required? What is the method? So 1 second divided by time of one machine cycle. How much it is? It is 1 second divided by what is the clock frequency? It is 1 over 8 megahertz, which is nothing but 1 over 125 nanoseconds. So this you get. Now this is the count value you are supposed to work out to compute the required value. So probably we can do a reverse engineering here. So we get a value something more than what is required. So we may get a larger value here. So this value comes around 8 into 10 to the power of 6. So this is the number required. So I should now compute this machine cycle. If I have to do, then I have to use one of this formula here. Okay, I should repeatedly use that so that this formula should match. Okay, whatever I am typing over here, this works out. This value should be 8 into 10 to the power of 6. You should find out a magic number here so that you can just map it and just use it. We will have a very deeper look into this, how to compute this. Probably I need to work out some example here to show you how this can be done. But so the mapping remains same. You should actually map this machine cycle information on this count. So this is something you can select these values, somewhat randomly, so that the product remains this. So that's about how we can actually use these instructions, call routines in the example, and use these delay functions and using all these jump instructions.